Hello. Tonight, we will discuss the vast and mysterious existence of black holes. Black holes are among the most mysterious and compelling phenomena in the known universe. Born from the collapse of massive stars or the accumulation of mass in the centers of galaxies, they exist at the very edge of scientific understanding. Where gravity becomes absolute, light is unable to escape, and time itself behaves in unexpected ways. The concept of a region in space where gravity is so strong that nothing, not even light, can escape its pull might seem like a product of modern physics. But the idea has deeper roots. It has evolved alongside the progression of human understanding, beginning with simple observations of the stars and culminating in complex equations of space-time. From ancient philosophers contemplating the heavens to today's astrophysicists detecting gravitational waves from distant mergers, the path to understanding black holes has been long, surprising, and deeply human. A black hole is not simply a void or an absence. It is a real object with mass, spin, and structure. It warps the geometry of space and alters the flow of time. Near it, matter is stretched and twisted, radiation is bent and scattered. Yet from a distance it behaves like any other object with the same mass. This paradox of being both familiar and utterly alien makes black holes a central subject in theoretical physics, cosmology, and even philosophy. Though black holes cannot be seen directly, their presence can be inferred through their effects. Stars orbit around invisible masses. X-rays stream from matter spiraling into nothingness. Ripples in space-time spread out from distant cataclysms where two black holes collide and merge. These are not abstract theories. They are observed events. They are measurable, tangible, and real. In recent decades, black holes have transitioned from theoretical curiosities to observed phenomena. In 2015, scientists at LIGO detected gravitational waves from a binary black hole merger over 1 billion light-years away, confirming a prediction of Einstein's general relativity. In 2019, the Event Horizon Telescope produced the first image of a black hole's shadow, a silhouette cast by light warped around the supermassive black hole in the galaxy M87. These achievements marked a turning point in the study of black holes, bringing them from the realm of equations into the domain of evidence. The story of black holes spans centuries and encompasses the contributions of some of history's most brilliant thinkers. Isaac Newton laid the foundation for gravitational theory. Jean Michel and Pierre-Simon Laplace speculated on dark stars from which light could not escape. Albert Einstein's theory of general relativity introduced a new understanding of gravity as the curvature of space-time itself. Carl Schwarzschild solved Einstein's equations to describe a spherically symmetric, non-rotating black hole. Later, Roger Penrose and Stephen Hawking expanded on these ideas, showing that singularities are not mathematical artifacts, but unavoidable consequences of gravitational collapse. Black holes are categorized by mass and behavior. There are stellar mass black holes formed by the death of massive stars, supermassive black holes anchoring galaxies, and intermediate black holes whose origins are still uncertain. Some theories suggest the existence of primordial black holes formed in the earliest moments after the Big Bang. Others propose white holes, the theoretical opposites of black holes, which might exist under exotic conditions. Despite the immense gravitational forces near a black hole, these objects follow the known laws of physics. Matter entering a black hole does not vanish without trace. It adds to the mass, increases the spin, and may contribute to its charge. Yet deep questions remain, particularly regarding what happens to information that crosses the event horizon. The information paradox, raised by Hawking in the 1970s, continues to drive debate about the fundamental nature of space, time, and quantum mechanics. Black holes challenge the boundaries of physics. They are laboratories where general relativity meets quantum theory, where the large scale of the cosmos intersects with the smallest particles and energies. They are not only a destination for falling stars, but a frontier for human understanding. The idea of black holes may seem like a product of modern physics, but its origins can be traced back to centuries before Einstein's theory of general relativity. The journey began not with telescopes or advanced mathematics, but with human curiosity about gravity and light, two forces that shape how we experience the universe. In the 17th century, Isaac Newton introduced his theory of universal gravitation. His laws described gravity as a force acting between masses, allowing predictions of planetary motion with extraordinary accuracy. Though Newton's model worked well for the solar system, it also led to a natural question. What if a body were so massive and its gravitational pull so strong that even light could not escape? This idea was first proposed in the late 18th century by John Michell, a British natural philosopher and geologist. In a letter to the Royal Society in 1783, Michell speculated about the existence of dark stars. According to Newtonian mechanics and the particle theory of light that was common at the time, a sufficiently massive object could exert such a gravitational pull that its escape velocity would exceed the speed of light. Light, pulled inward, would fall back to the surface. Though Michell lacked the means to detect such objects, his reasoning was theoretically sound. Around the same time, French mathematician Pierre-Simon Laplace independently arrived at a similar conclusion. In his 1796 book Exposition du système du monde, Laplace described what we might now call a black hole, a region of space where gravity would prevent light from escaping. These early concepts, however, were largely forgotten in the 19th century as the wave theory of light gained prominence, displacing the older particle model. For more than a century, the idea of a completely lightless object remained a philosophical curiosity. The tools of classical physics, while powerful, could not fully account for the nature of space, time, or the behavior of light in extreme gravitational environments. The next major breakthrough would not come from speculating about massive stars, but from a radical rethinking of gravity itself. In 1915, Albert Einstein published his general theory of relativity. Rather than treating gravity as a force, Einstein described it as the curvature of space-time caused by mass and energy. Massive objects like stars and planets distort the space around them, causing smaller objects, or even light, to follow curved paths. This framework not only replaced Newton's model on cosmological scales, but also opened the door to new predictions. The bending of starlight around the sun, the slowing of time in strong gravitational fields, and the possible existence of regions from which nothing could return. Just months after Einstein introduced his equations, a German physicist named Karl Schwarzschild found a solution to them. In the middle of World War I, From the Russian front, where he was serving in the German army, Schwarzschild derived an exact solution describing the gravitational field outside a spherical, non-rotating mass. This became known as the Schwarzschild metric. The Schwarzschild solution introduced a peculiar boundary known today as the event horizon, a radius within which the escape velocity exceeds the speed of light. Inside this radius, no signal or object could return to the outside universe. At the very center, the equations pointed to a singularity, a point of infinite density where the known laws of physics break down. Though mathematically valid, this solution raised philosophical and physical concerns. Many physicists, including Einstein himself, were skeptical that nature would allow such extreme outcomes. The idea of a singularity was troubling, suggesting an edge to physical understanding. For decades, the concept remained controversial, treated more as a mathematical artifact than a physical prediction. It was not until the mid-20th century that black holes began to gain acceptance as real astrophysical objects. In the 1930s, Indian-American astrophysicist Subrahmanyan Chandrasekhar showed that white dwarf stars, remnants of stars like our Sun, could not support themselves against gravitational collapse if their mass exceeded a certain limit, now known as the Chandrasekhar limit. His findings implied that massive stars might collapse into even denser states, possibly leading to neutron stars or something more extreme. Chandrasekhar's ideas were initially met with resistance, most famously from Arthur Eddington, who believed that nature would not permit such collapse. But over time, theoretical work and astronomical observations continued to point toward the existence of compact, invisible objects with immense gravitational pull. In the 1960s and 1970s, work by Roger Penrose and Stephen Hawking brought a new level of mathematical rigor to the study of black holes. Penrose developed the concept of trapped surfaces and showed that singularities could form under realistic conditions, not merely in symmetric, idealized cases. Hawking extended this work, examining the behavior of spacetime near singularities and contributing to the formulation of the cosmic censorship hypothesis, which proposed that singularities would always be hidden behind event horizons. The term black hole itself was first coined by physicist John Archibald Wheeler in 1967. Before that, such objects were referred to as frozen stars or gravitationally completely collapsed objects. Wheeler's term quickly entered both scientific literature and the popular imagination, capturing the essence of something from which nothing, no matter, no light, no information, could return. By the late 20th century, black holes had become not only a central topic in theoretical physics, but also a viable subject for astronomical observation. Powerful telescopes and radio arrays began detecting signs of compact objects in binary star systems. Jets of high-energy particles from galactic centers pointed to active black holes millions or even billions of times the mass of the Sun. What had once been a speculative idea was now becoming an observational reality. The history of black holes reflects the broader history of science. The movement from intuition to mathematics, from philosophy to data, from mystery to understanding. It is a story marked by persistence, creativity, and the willingness to explore ideas that once seemed impossible. From Michel's dark stars to Schwarzschild's singularities, from Einstein's curved space-time to the first photographs of a black hole shadow, the evolution of this idea reveals much more than just the nature of gravity. It shows how human thought, when given enough time and freedom, can peel back the layers of the universe and illuminate even its darkest corners. At the beginning of the 20th century, physics stood at a crossroads. Classical mechanics, built on the foundation of Newton's laws, had described much of the physical world with remarkable precision for over 2 centuries. Yet troubling anomalies were beginning to emerge. Light behaved as both wave and particle. Mercury's orbit deviated slightly from predictions, and gravitational interactions, though precisely calculated in most contexts, lacked a deeper, unified explanation. Into this growing tension stepped Albert Einstein. In 1905, he introduced the special theory of relativity, showing that time and space were not fixed quantities, but relative to the observer's motion. Time could dilate, lengths could contract, and the speed of light was the same for all observers regardless of their own velocity. This was revolutionary, but it addressed only the case of uniform motion, objects moving at constant speeds in straight lines. The deeper problem of acceleration, and especially gravity, remained unresolved. Einstein would spend the next decade grappling with that problem. His insight, born from a thought experiment involving a man in free fall, was that gravity could be understood not as a force, but as a geometric property of space-time itself. If a person in an enclosed elevator were falling freely, they would feel weightless, no different from floating in space. This led to the equivalence principle, the idea that inertial and gravitational mass are indistinguishable. Gravity, Einstein concluded, was not a mysterious force reaching across space, but the result of mass curving the very fabric of space-time. In 1915, after years of development and refinement, Einstein presented his general theory of relativity to the Prussian Academy of Sciences. The central idea was elegant and profound. Matter tells space-time how to curve, and curved space-time tells matter how to move. Instead of forces acting at a distance, objects follow the natural paths, called geodesics, within a curved geometry. The equations governing this relationship, known as the Einstein field equations, linked the distribution of mass and energy to the curvature of space-time. The implications were vast. General relativity predicted that time would pass more slowly near massive objects, a phenomenon known as gravitational time dilation. It suggested that light would bend around stars, which would later be confirmed during a solar eclipse in 1991. It allowed for the possibility of dynamic universes, including expanding or contracting cosmologies, and, crucially, it permitted the existence of regions in space where curvature became so extreme that it formed a boundary beyond which nothing could return. Einstein himself, however, was cautious about these extreme consequences. The field equations were complex and difficult to solve, and Einstein believed nature would somehow prevent the formation of singularities, points where density and curvature become infinite. He regarded such outcomes as mathematical curiosities, not physical realities. That view began to change almost immediately. In December 1915, just weeks after Einstein finalized his equations, Carl Schwarzschild found the first exact solution. He had been serving as an officer on the Eastern Front during World War I, yet managed to derive a solution describing the space-time outside a spherical, non-rotating mass. His solution revealed a key feature, a critical radius, later called the Schwarzschild radius, within which the equations break down and strange behavior occurs. Time, as experienced by an outside observer, would slow to a crawl near this boundary. The curvature of space would become extreme. Though Schwarzschild himself died of illness just months after his discovery, his solution marked the first theoretical description of what would later be called a black hole. For decades, physicists debated whether such objects could actually form. Would collapsing matter truly shrink below the Schwarzschild radius? Or would some physical mechanism prevent it? Einstein remained skeptical. In 1939, he published a paper arguing that black holes were unlikely to exist in nature, but not everyone agreed. That same year, J. Robert Oppenheimer, later known for his role in the Manhattan Project, and his colleague Hartland Snyder published a paper demonstrating that, under general relativity, a sufficiently massive star could indeed collapse to form what they described as a frozen star. From the perspective of a distant observer, the collapse would appear to slow infinitely as it approached the event horizon, while from the falling object's own point of view, the collapse would proceed to completion. The term frozen star captured the strange nature of black holes in relativity. To an outside observer, objects appear to freeze as they approach the event horizon due to time dilation. Yet this is only an illusion. From the perspective of the infalling matter, the collapse continues until a singularity is reached. Despite these theoretical insights, black holes remained controversial. Many physicists considered them to be unphysical, or at best, rare and irrelevant to the broader universe. The equations of general relativity were rich and complex, but without observational confirmation, they remained speculative. The true power of Einstein's revolution was not fully appreciated until decades later, when astronomical observations began to suggest the existence of extremely compact, massive objects behaving exactly as black holes were predicted to. Einstein's general relativity had opened the door to a universe governed not by invisible forces, but by the curvature of space-time. It described how light bends, how time slows, how gravity warps the universe itself. And it introduced a new kind of object, not simply massive and luminous like a star, but dense, dark, and fundamentally strange. Black holes, as described by general relativity, were not holes at all, but regions of space with an extraordinary geometry. At their boundary, the escape velocity equals the speed of light. Inside, paths converge on a central singularity. Around them, light orbits in photon spheres. Beyond them, nothing returns. The story of black holes took a pivotal turn in 1916 when Carl Schwarzschild found the first exact solution to Einstein's field equations of general relativity. Despite the fact that Einstein had only recently published his theory, and while Europe was still gripped by World War I, Schwarzschild derived a precise mathematical description of space-time around a spherically symmetric, non-rotating mass. His work was extraordinary, not only in its insight, but in the context of its creation. He completed the calculations while serving as an artillery officer on the Eastern Front, and sent the solution to Einstein in a letter that would go on to change the future of astrophysics. The Schwarzschild solution describes a region of space-time that is perfectly spherical, static, and empty. except for a central point mass. From this geometry arises a radius that would eventually become one of the most defining characteristics of black holes, the Schwarzschild radius. This radius is not a physical surface, but rather a mathematical boundary. If a mass is compressed within this radius, it forms a black hole. For a mass equal to that of the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it is less than a centimeter. The fact that such a small radius could encompass such a large mass hints at the unimaginable densities required to create a black hole. At the Schwarzschild radius lies what would later be termed the event horizon, a boundary in space-time from which nothing, not even light, can escape. Unlike a solid surface, the event horizon is not made of matter. It is the mathematical edge of no return. Once an object crosses this boundary, it becomes causally disconnected from the rest of the universe. Its information, energy, and motion are hidden behind a veil that no observer outside can penetrate. To understand this boundary, one must consider how time and space behave near it. In general relativity, gravity is not a force but a warping of space-time. Near a massive object, time slows down relative to a distant observer. As an object approaches the event horizon, time dilation becomes extreme. From the viewpoint of someone far away, the falling object appears to slow and freeze at the horizon, never quite crossing it. However, from the object's own frame of reference, it passes the horizon in finite time, continuing toward the singularity at the center. This duality, where an event occurs in one frame of reference but appears frozen in another, is a direct consequence of the geometry described by Schwarzschild's solution. It's one of the most counterintuitive aspects of black holes. From the outside, the event horizon is a static sphere. From the inside, it is a one-way surface, and passage through it is irreversible. Although Schwarzschild's solution was exact and elegant, its implications were initially misunderstood. Many early physicists viewed the singularity at the Schwarzschild radius as a sign of mathematical failure. Even Einstein believed that the theory broke down at this boundary and that nature would not allow such objects to exist. In reality, the Schwarzschild radius itself is not a physical singularity. It is a coordinate singularity, meaning it arises due to the choice of coordinates used in the mathematical description. The true singularity lies deeper, at the very center of the black hole, where the curvature of space-time becomes infinite. This central singularity is a point of zero volume and infinite density, where all known laws of physics cease to function. What lies at or beyond that singularity remains unknown. Later work in the mid-20th century, particularly by David Finkelstein and others, clarified the nature of the event horizon. Finkelstein described it as a causal boundary, a surface through which signals can pass inward but never outward. It is a one-way membrane in the fabric of space-time. Once crossed, the path to the singularity is inevitable. Nothing inside the event horizon can influence events outside of it. The Schwarzschild solution also predicted the existence of photon spheres, regions just outside the event horizon where light can orbit the black hole in unstable circular paths. These orbits are a consequence of the extreme curvature of space-time. A slight disturbance will cause photons to either fall into the black hole or escape to infinity. The photon sphere contributes to the shadow of the black hole, the dark region surrounded by a bright ring of gravitationally lensed light, as seen in the Event Horizon Telescope's image of the black hole in M87. The mathematical description of the Schwarzschild black hole is surprisingly simple in form, yet rich in implications. It describes a static, non-rotating, uncharged black hole. Real black holes in the universe are more complex. They can spin, they can have electric charge, and they can exist in dynamic environments. Yet the Schwarzschild solution remains the foundational model from which all others extend. In time, physicists would expand on Schwarzschild's work. The Reissner-Nordström solution describes charged black holes. The Kerr solution, discovered by Roy Kerr in 1963, describes rotating black holes. These more general solutions reveal additional features, such as ergospheres and frame dragging, where space itself is twisted by the black hole's rotation. But at the heart of all these developments is Schwarzschild's original insight, that the geometry of space-time can fold in upon itself, creating a region from which nothing can escape, governed by mass and bounded by an invisible horizon. Schwarzschild never lived to see the legacy of his work. He died in 1916, just months after submitting his solution from an autoimmune disease contracted during the war. Yet his contribution endures as one of the most important in modern physics. His name is now synonymous with the simplest type of black hole, a theoretical object that proved to be not only mathematically consistent, but also physically real. The Schwarzschild solution transformed black holes from hypothetical oddities into mathematically sound possibilities. It provided the first glimpse into how space-time behaves under the most extreme conditions, and it laid the foundation for the exploration of a cosmic frontier that would continue to expand for the next 100 years. The universe is a place of balance. From the faint glow of a distant nebula to the radiant brilliance of a star, everything exists in a delicate equilibrium of forces. In the case of stars, that balance lies between the relentless inward pull of gravity and the outward push of radiation pressure created by nuclear fusion. For millions, even billions of years, this equilibrium holds steady. But when the fuel runs out, the balance breaks, and in some cases, what follows is the birth of a black hole. Stars begin their lives in vast molecular clouds, regions dense with gas and dust. Under the influence of gravity, these clouds collapse and fragment into protostars. As the core of a protostar heats, nuclear fusion ignites, converting hydrogen into helium and releasing tremendous amounts of energy. The radiation pressure generated by this process pushes outward, resisting further collapse. The more massive a star, the greater the pressure and temperature at its core. In stars more than about 8 times the mass of the Sun, the fusion process proceeds beyond helium, synthesizing progressively heavier elements: carbon, oxygen, neon, silicon, and eventually iron. Iron is a turning point. Unlike previous elements, the fusion of iron does not release energy. It consumes it. This is due to the nuclear binding energy curve, which reaches a peak at iron. As iron builds up in the core, fusion stalls. With no more outward pressure to counteract gravity, the core becomes unstable. The result is catastrophic. In a fraction of a second, the iron core collapses under its own gravity. Electrons are forced into protons, forming neutrons and releasing a flood of neutrinos. The core becomes incredibly dense, so dense that it reaches the density of atomic nuclei. At this point, the collapse halts, and the outer layers of the star rebound off the newly formed neutron core in a titanic shock wave. This explosion is known as a supernova. It is one of the most energetic events in the universe, capable of briefly outshining an entire galaxy. The outer layers of the star are blown into space, enriching the cosmos with heavy elements, carbon, gold, uranium, and more, the building blocks of planets, life, and future stars. But what remains at the center is even more fascinating. If the remnant core has a mass between about 1.4 and 3 solar masses, it becomes a neutron star, an object of unimaginable density, composed almost entirely of neutrons. A teaspoon of neutron star material would weigh billions of tons. However, if the core is more massive than this critical limit, around 2.5 to 3 solar masses, gravity overwhelms even neutron degeneracy pressure. No known force in nature can resist the collapse. The result is a black hole. This process is known as stellar collapse, and it is the most common path to black hole formation. The newly formed black hole is a region of space-time containing all the mass of the stellar core, compressed into a volume so small that the escape velocity exceeds the speed of light. The boundary of this region is the event horizon. Anything crossing this threshold, matter, energy, even light, is irrevocably pulled inward. The material continues to collapse inward toward the singularity, a point of infinite density and zero volume, where classical physics breaks down. From the outside, however, the black hole is remarkably simple. According to the no-hair theorem, a black hole can be fully described by just 3 observable properties: mass, electric charge, and angular momentum. All other information about the matter that formed it is effectively lost to the outside universe. This simplicity is deceptive. In reality, the formation of a black hole is a violent, complex, and dynamic process. Stellar material swirls inward in accretion disks, heating to millions of degrees and emitting intense X-rays. Magnetic fields twist and snap. Shock waves ripple through the surrounding interstellar medium, and gravitational waves, ripples in space-time, carry energy across the universe. Not all black holes form from the collapse of stars. Some may have formed in the very early universe, shortly after the Big Bang. These primordial black holes, if they exist, would be tiny and exotic, formed from density fluctuations in the early cosmic soup. Others are far more massive than any single star could create. These are supermassive black holes, found at the centers of galaxies, with masses ranging from millions to billions of times that of the Sun. Yet even the largest black holes may have begun with collapse. One hypothesis is that successive generations of stellar mass black holes merged over time, gradually building up to supermassive scale. Alternatively, massive black holes may have formed directly from the collapse of enormous clouds of primordial gas in the early universe. Stellar collapse is nature's gateway to the formation of black holes. It is the moment when the balance of forces fails, when gravity asserts its ultimate power, and when the known laws of matter are bent, stretched, and finally broken. In these final moments of stellar death, the cosmos creates one of its most enigmatic and powerful objects, a region where space-time itself is twisted into a one-way path toward the unknown. Not all black holes are the same. While the defining feature of every black hole is the event horizon, the point beyond which nothing escapes, these cosmic objects can differ dramatically in size, mass, origin, and environment. Over decades of theoretical development and astronomical discovery, scientists have identified several distinct classes of black holes, each with its own formation pathway and characteristics. These are broadly categorized as stellar mass, supermassive, intermediate mass, and primordial black holes. Stellar mass black holes are the most common variety observed in the universe today. They form from the gravitational collapse of massive stars at the end of their life cycles. When a star with more than about 20 solar masses reaches the end of its fuel supply, it undergoes a core collapse supernova. If the remaining core is heavy enough, it will continue collapsing until it becomes a black hole. These black holes typically range from about 3 to 30 solar masses, though in certain cases they may be somewhat heavier. In isolated conditions, it's rare to find stellar black holes much larger than this, because stars lose mass through winds and radiation over their lifetimes. However, in binary systems, black holes can gain mass by accreting material from a companion star. Stellar black holes are difficult to detect directly. They do not emit light. Instead, they are often discovered through X-ray emissions caused by matter falling into them from nearby stars, or by observing gravitational waves from collisions between two such black holes. These methods allow astronomers to estimate their masses and confirm their presence. At the opposite end of the scale lie supermassive black holes, SMBHs, with masses ranging from millions to billions of times the mass of the Sun. These behemoths reside at the centers of most, if not all, large galaxies, including our own Milky Way. The black hole at the heart of the Milky Way is called Sagittarius AI, and it has a mass of about 4 million solar masses. Unlike stellar black holes, the formation of supermassive black holes is still not fully understood. Their existence in the early universe, only a few hundred million years after the Big Bang, suggests that they must have formed rapidly. There are several hypotheses. Direct collapse of massive gas clouds early in cosmic history. Hierarchical mergers of smaller black holes over billions of years. Rapid accretion of mass through intense feeding episodes. SMBHs power some of the most energetic phenomena in the universe. When actively feeding on gas and dust, they produce quasars, extremely luminous galactic nuclei visible across vast cosmic distances. These objects can outshine entire galaxies and serve as beacons from the early universe, even when quiescent, supermassive black holes shape their host galaxies. Their enormous gravitational influence helps regulate star formation, redistribute matter, and potentially dictate the structure of the galactic core. Long hypothesized but elusive intermediate mass black holes, IMBHs, fill the gap between stellar mass and supermassive black holes. Their masses range from around 100 to several 100,000 solar masses. IMBHs are believed to form through various mechanisms. The merger of many stellar mass black holes in dense star clusters, the collapse of massive population 3 stars, the first generation of stars in the universe, runaway collisions of stars in young stellar nurseries. Evidence for IMBHs is emerging slowly. Some candidates have been identified in globular clusters and dwarf galaxies through unusual X-ray signatures and gravitational wave events. One significant detection came in 2019 when gravitational waves from a collision involving a 150 solar mass black hole were observed, suggesting that at least some IMBHs form from mergers. Despite progress, IMBHs remain mysterious. Their detection is challenging because they are less likely to be surrounded by bright accretion disks or active galaxies, and thus emit far less radiation. However, as gravitational wave observatories become more sensitive, more IMBHs may be revealed. Primordial black holes, PBHs, are hypothetical objects that may have formed in the earliest moments after the Big Bang. Unlike the other classes, these black holes would not have formed from stars or matter collapse, but rather from quantum fluctuations or density irregularities in the high-energy environment of the infant universe. The masses of PBRs could span a wide range. Some may have been as small as asteroids or atoms. Others could have been large enough to rival stellar or even intermediate mass black holes. Tiny PBHs would have unique behavior. According to Hawking radiation theory, small black holes emit particles over time, gradually losing mass. If PBHs were created with very low masses, they may have already evaporated completely, releasing bursts of energy in the process. Larger ones could still exist today, hidden across the cosmos. Primordial black holes are a topic of intense interest because they might account for some or all of the dark matter in the universe. They could also explain certain anomalies in cosmic background radiation or contribute to the black hole merger rates observed in gravitational wave astronomy. As of now, no conclusive evidence has confirmed the existence of PBHs, but research is ongoing. Future high-precision surveys, such as those conducted by the James Webb Space Telescope, gravitational wave detectors, and cosmic ray observatories, may yet uncover them. Black holes span a truly vast range in mass and influence. From the collapse of individual stars to the swirling hearts of galaxies, they are present at every scale of the universe's structure. Each type offers a different perspective on cosmic evolution. Stellar mass black holes teach us about the life and death of stars. Supermassive black holes illuminate galaxy formation and early cosmic history. Intermediate mass black holes may link the smallest to the largest. Primordial black holes could reveal conditions just moments after the Big Bang. Despite their differences, all black holes share a common essence: the extreme warping of space-time, the irreversible nature of their horizons, and the deep mysteries they pose for the laws of physics. As scientists continue to observe, simulate, and probe these objects, each type of black hole contributes a piece to the larger puzzle. The more we learn, the more we realize how integral they are to the universe's architecture, not as outliers, but as fundamental structures woven into the cosmic fabric.